very cool.
Okay, and I didn't get your guy's name, so I'm just going to say open source three-phase motor controller.
Without our names on there, yeah. I'm Cameron Tacklin. This is my father, Chris Tacklin. My brother's even here too. So we have two microphones? Yes, we do. I think we do. So thanks for coming out. And tonight, Cam and I just wanted to share something we're working on that we want to make available to everyone. And it was inspired by the fact that we all know how to use all these various kinds of motors, and most of you are all experts on all these things. And but we also know from our friends that fly model airplanes that there are these incredible motors out there. They're incredible power density. Last time I did a robot that had a 250 watt motor. It was this big around, that long. Cost $130 just for the motor. This is 250 watts and it costs $17. And another part that's so great about it, that we know from our model airplane friends, is that the controller for it, this little stack of FETs and a little processor, that's $20. You control it with the same servo commands. But the only problem is if you want to use this kind of motor for precision control, so we want servo things, we want to position a motor, that you need to have sensors. And when you go to a fancy censored motor, suddenly the price jumps through the roof. Last time I bought some censored three-phase brushless motors for a work project, they were $1,000 a piece. And that's just ridiculous. And that means that our whole community doesn't have access to this kind of power because it's just way too expensive right now. And there's nothing in there. So we want to fix that. And so the way it's usually fixed is to buy a motor that has three Hall effect devices in it. This is all common to everybody? Yeah? Yeah. So you can get a motor that does have sensors in it. And if you have the sensors, you get three different square waves out that are 120 degrees out of phase. And you can use those to do some simple logic and decide what leg to go high, what one goes low. And that works pretty well. And in fact, you can do that without a computer. In the old days, I think it was done with optical encoders. But if you want to do that, it's still really hard because now you've got to make a little flag and some optical encoders. You got to get them all aligned just right. Or you can use Hall effect devices, I mentioned. But what you really want to do is send these beautiful brushless coils, no brushes anywhere, nothing rubbing anywhere. You just want to send it these three beautiful sine waves. And if you could just send those beautiful sine waves, that beautiful motor would just spin. And we're all very familiar with how to make a computer make sine waves. Ken?
That's wrong.
So
Close enough. This.
Close enough. Well, so it turns out, of course, you can make sine waves with a computer. And Cameron noticed that a particular Atmel that he came across that had exactly the right hardware for making beautiful sine waves.
And I guess I'll just get started here. So in particular, it's the Mega 32U4 that some of you might be familiar with from the Arduino world. There actually are a couple other Arduinos that have similar features. But the important thing, USB is nice, but the really important thing is this high-speed timer. And with a 10-bit timer and running at 64 megahertz, we can actually get 32 kilohertz PWM. That's above the audible range, and so ideally you can't hear the motor, which is nice. And we get 6 PWM controllable outputs that actually have adjustable dead time, hardware controlled, software set, but hardware generated and everything. And so that was a prime processor to get started with this project.
That's a little unusual. This was a particular processor that has that, but it's a common part.
So the goal was to first just generate 3 sine waves. And we all know what sine waves look like, pretty obvious. But with 3 H bridges, you can't just put out 3 sine waves and have it work. Maybe you could. But we actually, with a delta motor, one of the legs you always hold it ground. And so you need to simulate or do the right thing to the other 2 legs to get the sine wave. And I did that work, and you can see these funny little bumps in the,
for one phase temporarily goes up and comes back down, and comes back up and comes down, and then is held at 0. And that's just how you can get sine wave out. That's basic stuff.
Is that clear? Just you want the difference between the phases to have that sine relationship, so their absolute value voltage doesn't matter. And so for practical purposes, it turns out you leave one of them just locked to 0, and then the other two do the PWMing, and you get the same voltage from one phase to the next as a full sine wave.
And so people have done this before. People have generated sine waves. This is nothing hugely new, but we're doing it with some cheaper chips, which is a little nice. We have a lookup table to just do that sine wave, and we have to just get the piece of sine that we need and replicate it a couple times, which is really nice. But then the real killer part is we need to know where the motor is to do this, put the right sine wave out. And we don't want to use those, what we consider expensive, built-in Hall effect sensors. And so we realized,
Or expensive, high-resolution incremental encoders.
exactly. And so we realized there's a really nice part from Alexis. There are a couple of companies make equivalent parts. It's actually a 3 degree of freedom magnetic field sensor.
It's actually a Hall effect device.
It is a Hall effect device, but it's giving us, it's internally doing 3 degrees of freedom. It's actually doing that inverse tangent for us and giving us an absolute angular position out at 12 bits of resolution.
So this is a great encoder we use on a bunch of projects, and it should be clear from this little illustration from their website that if you just put a magnet in front of this chip that's radially polarized, you put this on a wheel on a robot, and so as that magnet moves around, that sensor gives you an analog value out or a number out that's related to the angle of that wheel. Just boom, done, nothing to align. It goes right through plastic, it goes through water, and they're cheap, and they're digital interface, SPI, and with a kilohertz update rate and 10-bit or 12-bit resolution. So for $3, you can get 4,000 counts per revolution of your wheel, and with no alignment. That's magic for me. I just love it. So we use it all the time.
Yeah, so we've been using the sensor for a while for other things, but with this we can go straight to the next step of how do you actually drive 3 sine waves in phase with the motor, how the motor wants them. And so the first thing we actually did is we just generate open loop 3 sine waves, just start going really nice and slow. And we had that going at like 1 RPM kind of thing.
Yeah, and we include this bicycle crank here just for analogy. So if you're pushing on a bicycle crank, it's always going to go to the bottom. And when you change the set of phases you have, it's like you suddenly have a new crank that's over a little bit of an angle, and you're still pushing down, and so it goes to the bottom. Does that make sense? And so by rotating the phase slowly, the motor's always going to the bottom, and so it's telling you exactly how the phase lines up with the physical position of the motor and that encoder. And if you run it backwards, you should get the same thing. So,
And so here, I did that, and here, orange is the ideal line, blue you can see some nonlinearities.
this
actually
yellow
goes forward.
is a fit to all of it.
No, orange is the commanded angle.
Right.
So this is not, I have not.
You're right. So,
Anyway. And here, you can see the graph looks exactly the same for reverse. It's slightly off-center, and so I just averaged those 2, and now I have an angle from my magnetometer that correlates to the 3 sine waves that I need to put out for pushing in the most inefficient way.
useless way, yeah.
And so from there, you can pretty quickly calculate, we actually want to push 90 degrees out of phase to get maximum torque.
All right, so on a bicycle, you always want to push when the crank is straight out, right? Because you're pushing straight down. And so we electrically determined where this was. So you just have to subtract 90 degrees, and that's what your phase should be. If you're at this position, this is what you got to output, and it'll go. And if you want to go the other direction, you just have the phase over here, and the motor goes in the other direction. It's that simple.
And it turns out you didn't even need to make it perfectly match the real data, because 90 degrees plus or minus cosine error is going to be nothing. So anyway, without further ado, I coded that. I've got a little processor, I've got some FETs, and I've got the magnetometer, and I've got it hooked up to a little hardware here. And right now I'm just, as fast as possible, reading the current position.
Before you do that, well, so just to reiterate, so here's this nice little motor, it was 15, 17 bucks, something like that.
And here's this gorgeous little circuit board that Cameron made. That's our third generation probably. And if you come and look later, right in the center of the circle is that little Melexis chip, little 8-pin sock. And then there's plenty of room for a processor and a little stack of FETs. And that just mounts, just bolts right to the back of the motor. That's it. That's all
It
it's
doesn't
on.
even have to be aligned.
No alignment at all. Because the phase alignment is going to be constant, but once you run the motor once, now you know exactly what the map is. You're all done.
And so here we go. I just had a little demo ready to go. Turn this on. This is running at 1% torque or 1% PWM, and it's. Have you ever seen a brushless DC motor run at that low speed and still put out pretty constant torque? Actually, it's not running constant torque. That's the square wave output. Sorry, that's 1%. And I will let you all come up and feel this later. It's a lot more impressive if you can feel it. It's a rather smooth torque ripple.
If you've ever ridden an electric bike at low speeds, at least the ones that I've tried with three-phase motors, using that square wave, you can feel as it starts up, it goes, as those square waves are going by. It's as though you're a crank, you're always pushing the same phase, or the same torque, or same force, regardless of the angles. You're not getting that beautiful sine wave motion. And so Cameron's rigged the software so each time it cycles the power, it'll go to a different mode tonight. So one of the modes will be a square wave. You can feel, and another mode is sine wave, and it's just almost as smooth as silk. It doesn't cost any more.
And so that basically wraps up the state of it now. And on to what our future goals are. I would like to make this open source. I want more people to help. I want other people to.
There you go.
What?
Go
I guess I'm jumping ahead of myself. There are a couple things that still need to be done, and I would welcome help to get done. I can do my own, but it'll just take a lot more time. Things that I haven't done yet is some FET optimization, driving those, picking the right resistors, picking the right size FETs. I think I have 30 amp FETs on there right now, and I'm only using an amp. But theoretically, I can go higher. It's also totally capable. We can use back EMF and switch over to back EMF when you get up to velocities that are too high for the magnetometer.
That's actually something that we left the slide out, is that since this encoder is absolute, you only need to check its position twice per revolution. All right, so if you look at the maximum speed for these beautiful, very fast motors, and if you only have to check twice per revolution, that's plenty fast to always to know where that thing is all the time, almost. I think it's up to 80% of the motor speed. But if you had a 4,000 count per revolution encoder, trying to keep up with that, you'd have to be doing that 2,000 times or 4,000 times faster. Which you could do the hardware to do that, but it's just a lot more trouble.
So, Chris or Cameron? So yeah, I wanted to ask a little bit about the speed versus the sampling rate. So you said your magnetic encoder gives you a reading at a 1 kilohertz rate?
Yeah.
That's the maximum. So wouldn't that limit you to 500 RPM then if you say you need 2 readings per?
Yeah, and I think if you run the numbers on this particular motor, we're just under that, so we can get 2 readings for the RPM limit of this motor in this setup. But I fully intend to be able to switch to back EMF when you get to high velocity.
It's
Okay.
revolution, it's
500
confusing.
revolutions per second.
Yeah, you're confusing seconds
revolutions
with
per
minutes.
second.
Right.
Yeah.
Yes,
Thanks.
And
yes,
actually,
sorry.
we forgot to put in a slide of,
Thousands RPM.
yeah. So we forgot to put in a slide, a fun thing we came across is that, you're right, 1 kilohertz update rate is pretty slow. And if you're accelerating, or you know that the phase that you put out now isn't going to be right 10 milliseconds later, or millisecond later.
Yeah.
And, but that's okay, because you know what your velocity is. And so Cameron's actually coded in an open loop. I'm going to just open loop change my phase according to what my velocity is right now. And when you get to the other end of that interval, you're going to be wrong a little bit. So you just adjust it and you keep doing basically a phase lock loop to keep your phase locked up.
How does it handle load disturbances and variable torque?
It doesn't care. Because it only depends on the position of the motor.
And that'll be very dependent on the control law and how it seeks to that new
Ah,
velocity, which I haven't optimized at all yet. This right now is kind of the first bit that got working, and so there's still a lot of room to optimize that phase lock loop. And
Yeah, that's
there's
just one of the
a
nets.
whole second set of things to
Well,
do.
two other sets of problems. One will do more advanced motor control stuff. But of course, this is all just kind of the real nitty gritty, doing the job that those carbon brushes used to do for us, right? And this has nothing to do with all the closing a servo loop or command or servo into a velocity or position. But there's plenty of room left in that processor to do all of that. And of course, the processor can communicate any way you like. This one has USB built into it. I2C is what we're using. You could use anything you want to communicate with it, including communicating with it with the normal pulse commands that we use for model radios. Right? You just send it one of those pulse commands, close the loop right on that board to position that motor, including having external sensors. Like you've got your motor here and your gearbox, but there's a potentiometer that's measuring the position of your arm someplace else. You can close the loop around that encoder as well. So it really opens up all this new stuff that we could do almost turnkey.
Are you guys using any kind of current controlled feedback on the motor, or are you guys just using the phase and
Good question. You have a slide on it? Or is it too late for that? Or too early for that?
Are you getting to the field-oriented control stuff, or?
both that and the using the current sensor to check the current that you're putting into the motor?
So right now, I'm just doing pure PWM. I haven't added the hardware to do that. This particular EVR has a bunch of nice hardware to deal with current stuff as well. And also, like, if it goes over current, automatically shut down. Haven't done any of that stuff. But yeah, actually, almost forgot. The next step, because we have a whole piece of hardware here, we know what angle we're at. We have a good estimate of what angle the motor's actually at, even though our updates are coming in at kilohertz. We can do that next step that people are talking about a lot now with ID and IQ control or field-oriented control or.
Did you have a slide from Albert?
Yes. And so I forgot about that.
So one of our colleagues, our office, is a real motor designer. Let's see, where's his hand? There he is. And he really understands the nitty-gritty of how these things work, and it's down to the field level of what's going on. And there's so many people out there that are working on trying to understand this and publishing papers, making specialized motor controllers, where you've got this chip that for $10 that has a bunch of secret stuff hidden in it, where that group of people decided that's what they were going to do, but of course they won't tell you what they did. And so the point of all this is to blow that open. We all can afford the processors. We can make these boards ourselves. We're going to find some way of making these boards available to whoever wants them. And so now we can start iterating on how are we going to do motor control. How are we going to start implementing this sophisticated stuff, but from the people that really understand it, and put it in the hands of everybody.
In particular, how can we logically explore this space of phase advance relative to the motor? So when I was saying I'm pushing 90 degrees forward, that's this 0. And you can actually phase advance further from that and get more torque, and more current, of course, in certain cases.
Let's just say
that might be
basically-
desirable.
It's just conceptually, remember I described this open loop, making sure the phase was in the right place while you're not looking. But yeah, if you're running at a certain speed and you're running at 90 degrees, maybe there's something sophisticated going on where you got to run them at a few degrees earlier. And I don't need to understand what all that sophistication or what the exact angle is. I just need some way of implementing it, and with this processor, of course, we can, according to what the experts tell us. Or we can do it experimentally, find out what the right phase advance is. So it's an extra little twiddle on that plus or minus 90.
We do have this one more. Do you want to add something here?
No, I'm going to make Albert talk about it if. There's just a picture, so just close up, you can't see it back there. So there's that nice little teardrop shaped board. It's teardrop so we can put on this little swingy arm that we're using. And we made it the same size of this particular common hobby motor. But we've also applied it to other kinds of motors because we just need that sensor, all right, and bring it out to the same code. And so we've done it on bicycle wheels. It's a Crystal Light 2,000 watt motor. And this is a motor off of a hoverboard. We got those little hover boards in the lab. It lasted 10 minutes before we broke it. There's some great parts in there. And even though this has a Hall effect, 3 separate Hall effect sensors, it turns out if you just take one Melexis device and glue it onto its board, it actually sees these magnets coming by. And since they're polarized opposite each other, the Melexis sees the sum of those, and so it looks like a rotating magnetic field. And so without even adding magnet, we can measure the position of the wheel. And the biggest surprise was the fields from the coils does not interfere. I didn't expect that. Do we have anything else?
Yeah, I jumped ahead earlier, but yeah. So we want to know what the next steps are. Welcome.
Yeah, so
Awesome.
Cameron's going to put all this in his GitHub. So the schematics, we have plenty of boards if anybody wants them. We're doing new revs all the time, trying to make it better, what the next one might be. But of course, the code's changing every night. So.
That should do it, I think.
If you have time, you can 2 minutes to come feel this.
Well, we can come out. People can
Well,
come
what
after.
we're going to do is we're going to break for 5 minutes.
Right, yeah, during that 5-minute break.
During
If
the
you want to
5-minute
come
break.
feel this.
And we can have it open after the next talk as well.
Excellent,
Where's the
absolutely.
URL for the GitHub?
I'm Cinderblock. It's not on there yet.
Someone has to
We'll
raise their hand.
distribute it to the club when it becomes
Yeah.
available.
And also is your PowerPoint available
Sure,
online?
sure, sure. Well, we haven't published it, but
Okay.
I guess we could put it on.
Well, when you publish it, just send us a link to the club mailing list and then we can see it, okay? Thank you.
So thank you very much.